Okay, what we're going to do in this podcast is take a little bit closer look at the idea of using light to describe the structure of the atom. We touched on this in the last podcast when we talked about the photoelectric effect, the wave-particle duality of atoms, and then we started talking about electromagnetic radiation in terms of frequency, energy, and wavelength. So we're just going to look at those four variables a little bit closer. Okay, let's take a look at the continuous spectrum. Just wanted to make sure my pen was okay there. Okay, as you know, light is made up of different wavelengths. In other words, white light that you see from, say, a light bulb, or the light that shines through the window, or sunlight, is made up of the different colors of the rainbow. And that's where we get the designation Roy G. Biv: red, orange, yellow, green, blue, indigo, violet. So after it rains and the sun comes out and you see a rainbow, you're simply seeing that white light being scattered through the raindrops, which is acting like a prism, breaking that white light up into its individual colors or wavelengths. So what we talked about in the last vodcast is if you were to take an atom and do the same thing. In other words, if you could break up the energy given off from that atom into its different wavelengths, you would get what we call the emission spectra. So what we said was, let's say for example you took a hydrogen atom which has one proton and one electron in that first energy level. My energy levels are terrible. So let's say you put some energy into that electron, and here you see we're putting a high voltage into a gas, and let's just assume this is hydrogen gas. So what happens when you put energy into that electron can jump up to an energy level, it can fall back down, and it will release a certain amount of energy. That energy has a corresponding wavelength which will correspond to a certain color. If you put more energy into it and it jumps up to the second energy level, it can fall back, or the third energy level, it can fall back to the second or fall back to the first, and again, it can release those specific energies which correspond to different wavelengths. Now remember, what we said about the Bohr model is these energy differences are specific. In other words, you can't just put in a random amount of energy, it has to be a specific amount of energy. That's why when hydrogen's one electron falls from specific energy levels, it will release specific wavelengths of light corresponding to that atom. And as we said back in the last vodcast, the line spectrum or emission spectrum is the fingerprint of that individual atom. So we talked a little bit about the four variables: wavelength, frequency, speed, and energy. Let's just go into a little bit more detail with these and write some equations. Okay, wavelength, frequency, and energy and speed are all connected. They're connected through a series of equations. So let's write them here. Wavelength is going to be equal to c over frequency. Now c is the speed of light, and it's 3 times 10 to the 8th meters per second. The speed of light is constant in a vacuum, and we're just going to assume that we're talking about a vacuum here. If you were to put light through a different medium, such as water, it would slow down a little bit. But we're going to assume we're talking about a vacuum, such as space. So whenever you see c in an equation, you're using that value. That's why we call it a constant. It stays at that value. Now remember, that's the symbol for wavelength, and that's the symbol for frequency. So if you rearrange this equation and solve for frequency, you would have frequency is equal to c over lambda. Now the one thing that you want to be careful here is oftentimes you're given wavelengths in nanometers. Now remember, since our unit for light is meters per second, and we want all of our units to be consistent, we always have to convert nanometers to meters. And remember, there's 1 times 10 to the 9th, nanometers in 1 meter. Okay, the energy calculation then is going to be E is equal to H times nu, or frequency. H is also another constant, and we refer to it as Planck's constant. If you do something wonderful in science, you'll get a constant named after you also. The value for Planck's constant, or Planck's, I typically call it Planck's constant, is 6.626 times 10 to the negative 34th, and the units are joules times seconds. And that is negative 34th there, not 39th. Okay, so H is a constant also. So whenever you see H in an equation, you're simply plugging in that value. Always remember to use your units also. Okay, so let's take a look at our diagram of the hydrogen atom again. Okay, so again, these lines represent the different energy levels, and as you can see, the jump from the first energy level to the second energy level is greater than from the second to the third, third to the fourth, etc. And as you can see, the energy for each of these jumps is equal to H times C over lambda. Because remember, frequency is equal to C over lambda. Whoops. So if we just put that into our E is equal to H times nu, so now we have E is equal to H times C over lambda, we have an equation to solve for energy. So what you're going to do is just simply solve for the missing variable in these equations. Where does this have application? Well, again, I think we mentioned in another previous vodcast, let's say you want fireworks and you want those fireworks to look red, blue, and white. What you're going to use are different chemicals that have different atomic structures, that when those electrons are ignited, in other words, when they blow up, those electrons will go to high energy levels, fall back down, and release different energies of light corresponding to the different colors that you see in fireworks. Okay, so let's do a couple of practice calculations. Let's say, for example, I told you that the wavelength of light is equal to 475 nanometers. The question might be, what's the frequency and what's the energy? So we're going to find those two variables. Now remember, the first thing we always want to do is put our wavelengths into meters. So 475 nanometers, let's multiply by 1 times 10 to the 9th nanometers in a meter. Our nanometers cancel. 475 divided by 1 times 10 to the 9th is 4.75 times 10 to the negative 7th meters. So now if we want to calculate our frequency, remember, frequency is equal to C over lambda. So C is 3 times 10 to the 8th meters per second. Whoops, that's an S. That's an S. Over what we just calculated, our wavelength, 4.75 times 10 to the negative 7th meters. When we do that, 3 times 10 to the 8th divided by 4.75 times 10 to the negative 7th, we get 6.32 times 10 to the 14th inverse seconds. Okay, first of all, if you cancel your units here, you finalize the math, your unit would be 1 over S. One way to write that is S to the negative 1. Remember, anything to the negative 1 is the reciprocal of that. Okay, so that's a typical number for frequency. 10 to the 14th is a very high number, but our frequencies will be very high. So if you were going to calculate the energy from that, energy is equal to h times nu, which is going to be equal to 6.626 times 10 to the negative 34th joules times seconds times our frequency, 6.32 times 10 to the 14th inverse seconds. Put that into the calculator, and we get 4.19 times 10 to the negative 19th. And our units, seconds will cancel, so we'll be left with joules. So the units there are joules. Okay, let's take a look at another set of equations. Let's say you said the energy is going to be equal to 5.46 times 10 to, let's say, the negative 19th joules. What's frequency and what's wavelength? Okay, so now since we know energy, and energy is equal to h times nu, we can rearrange this equation and solve for nu. So nu is equal to E over h, which is equal to 5.46 times 10 to the negative 19th joules over, okay, you're going to put that over h, which is 6.626 times 10 to the negative 34th joules times seconds. My 4 keeps looking like a 9, just realize that's a negative 34th. Okay, so put that into the calculator. 5.46 times 10 to the negative 19th divided by 6.626 times 10 to the negative 34th, and we get 8.24 times 10 to the 14th, and again, joules cancel, so our unit is inverse seconds. So now if we want to calculate wavelength, wavelength is equal to C over nu. C is 3 times 10 to the 8th meters per second. We just calculated nu as 8.24 times 10 to the 14th inverse seconds. Put that into the calculator, and you get 3.64 times 10 to the negative 7th, and again, our unit is going to be meters. That's going to correspond to 364 nanometers. You can do the conversion there if you would like to. Okay, so that's just a couple of practice equations, and then what we're going to do in the next podcast is take this idea of light and then apply it to what we call the quantum model.